ever wondered why it takes more effort to push a door closer to the hinge compared to pushing the door near the edge? Well, and this is explained by the rotational dynamic principle called torque. In this video, we will see what torque is and how it is applied in real-life scenarios. Where to begin? Torque is the measure of force causing an object to rotate around an axis, acting as a rotational version of linear force, holding similar rules and principles. For torque to be in action, it requires a force, an axis of rotation, the point in which the system is being rotated upon, and a moment arm, the distance from where the force is being applied to the axis of rotation. The units are in newtons meter, being a vector quantity, which the magnitude can be calculated with the cross product, which turns into torque equals to force times r, which is the distance between the lever arm and the force, and sine theta, which theta is the degrees between the lever arm and the force. The direction of torque can be determined with the right hand rule. Torque also plays a role in Newton's second law, as torque equals to the moment of inertia times alpha being angular acceleration. Torque also plays a role within the concept of work. We already know that work can be generated from a system from a position x of 1 to x of 2 through this integration formula. Now, a similar expression can be applied to torque with the rotating system from angle theta 1 to theta 2. Now we will go into an example. Let's say that we have a 200 gram mass placed on a meter stick 20 centimeters from the fulcrum. 170 grams mass is used to balance the system. How far will it have to be located from the fulcrum to keep the system in balance? We are given both the weight's mass and the position of the 200 gram mass from the fulcrum. To find the distance of the 100 gram weight away from the fulcrum, we will use the net torque equation to help us determine it. First, let's draw a force diagram labeling the forces acting upon the entire system. We can then set the axis of rotation on the fulcrum where the system is being rotated around. Then we can draw a torque diagram with the torque of the 200 gram mass and the 170 gram mass, but not the torque of the normal force, as it is on the axis of rotation. Therefore, we can set our net torque equation as this, where the 200 grams mass torque is negative with the help of the right hand rule. We can set this entire system equal to 0, where it is then we can determine that the torque of the 200 gram mass and the 170 gram mass must be the same in order to keep the system in balance. We can then expand the system and isolate the distance of the 170 gram mass. Since both of the forces are 90 degrees from the lever arm, sine theta can be then turned into 1. After plugging all the values into the calculator, we can determine that the distance of the 170 gram mass to maintain balance to the entire system must be approximately 0.2